now we will come back to Ising model, and we will study something which has a very fancy name, and Phil Anderson got the Nobel Prize for this in 70s for doing things like this. The idea is quite simple, so I want to introduce you to it. And we'll talk about broken symmetry and we'll talk about order parameters. So we will consider an Ising model. For an Ising model, the microstate is characterized by the values of these spins, right? You have to declare whether every spin is plus minus one, things like that, right? If you have all these values, you have the full microstate. Given this, the energy of an Ising model without any external field is going to be minus J Si Fj, right? And maybe this is nearest neighbor, maybe this is not, we leave it in the general case, and we assume J is site independent. J comes outside the summation. So you have something like this. So I'm gonna show you a puzzle and then try to understand what is the solution to that puzzle. So for the exam or at the end of this course, one thing you should be very confident with is calculating ensemble averages, right? So how do we calculate the ensemble average of anything in StatMech? We go to every microstate, we look at the value of that observable in that microstate, we multiply with the probability of that microstate, right? So in this, we're going to work with canonical ensemble. So our P nu will be given by e to the power minus beta E nu divided by some partition function Q, which is Q or Z, whatever you want to call it, which is summation of e to the power minus beta E nu. The point being that Q comes outside the summation. So Q comes over here, we go to every microstate, we do M nu, e to the power minus beta E nu. Okay, good. So let's call this as equation 1. Let's call this as equation 2. If you put, and what is M nu? M nu is going to every spin, I is equal to 1 to n, and looking at the moment of that spin, mu is just a scale. If it bothers you, you can set that equal to 1 multiplied by SI, right? This is the magnetization of the whole system. So given this, and we know that SI can be plus minus 1. And again, notice this is not talking about a 1D, 2D, this could be any Ising model. It's just a collection of spins. Given this, if I put equation 1 and 2, what I'm going to get for the average magnetization, that will be 1 over Q, summation nu, M nu, and now this E will become minus beta, will become plus beta, J summation Si Fj, right? And let's write down the value of M nu here. What is M nu? M nu is summation I is equal to 1 to n. Let's put mu outside, that is just a number, Si multiplied by e to the power plus beta j summation Si Sj. Okay, so here's the puzzle. If you had a microstate where the spins had certain values, S1, S2, S3, dot, 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 and you took this microstate and you flipped every spin in the opposite direction. Maybe some spin was plus, maybe some spin was minus, I don't care. But whatever it was, you make it the other thing. If it was plus, you make it minus. If it was minus, you make it plus. So you take this and you make it minus S1, minus S2, minus S3, dot, dot, dot. If you do that, what happens to this quantity? Summation Si Fj. That will stay the same because both of them are changing, right? It's not just you're changing only Si or only Fj, you're changing both of them. It's a product. Both have become minus, so that thing changes. What happens to this thing? It becomes negative, exactly the same thing, but negative. So if you think about M now, what should be the average value of M then? This is telling us the average value of M should be 0. Because any given spin configuration, if you flip it into its negative value, it has the same probability, right? The probability of this Hamiltonian stays the same. The energy of the microstate here does not change if you flip every spin. So every configuration, in other words, every configuration with, let's say, positive M nu is equal to summation mu Si will have a corresponding configuration with M nu equal to summation mu minus Si with equal probability. This is sort of bad news. What does this mean about average value of M? It should be 0 for all temperature, for all Ising models. That's kind of disaster. Does anyone see? First of all, do people see the puzzle? Why this happened? If I have no external magnetic field, the probability of observing SI/SJ is the same as probability of observing minus SI minus SJ. That probability is the same, but the magnetization is now opposite in sign. So +5 is equally likely as -5. +6 is equally likely as -6. I'm not saying that +6 is more likely than +5. All I'm saying is that they are going to be equally likely. So average magnetization is going to be 0. This is clearly not true. We saw this is true in 1D, right? Maybe this could be justified for 1D Ising model with not infinite range interaction. In 1D Ising model, we saw through the Pearl's droplet argument that average magnetization is 0 at any temperature. As soon as you go to the smallest possible temperature, everything goes to 0, right? In 2D, clearly, this is not the case. We have average magnetization at finite temperatures. You saw that in the Wang Landau team, right? And we saw that in our course also. Of course, we have a curve, average magnetization goes to 0. So we have a situation and we need to solve this. How do we solve this? The answer really comes from, so why do we have a situation? Because in 2D and 3D, average magnetization is generally not equal to 0 for finite temperature smaller than the critical temperature. There is a critical temperature above this, it can become 0, right? Until the critical temperature is not 0. So we need to solve this. In order to solve this, we really need to understand how did we prepare the system? And a lot of problems in physics and chemistry often boils down to how did you prepare your system? You might be running some fancy, complicated experiments. If you're sloppy in your system preparation, your work is crap, right? You can do whatever. You can be running some experiment on some laser spectroscopy, whatever you're doing. You need to do your sample preparation very, very quickly, right? You need to understand how did you get to the starting state of your experiment. If you're not careful, everything is wrong. In fact, David Chandler had a fight till his deathbed with someone named Pablo De Benedetti, who is at Princeton, about whether water has 2 phases or not, liquid water. And it got really, really ugly and controversial. American Journal of Physics Today has an article on it, how bad it was. And Chandler was wrong. Chandler's system was not equilibrated correctly, and Pablo De Benedetti won the bet. So I have a story. One time I met Pablo somewhere and he said, I want to come to Maryland to give a seminar. And John Weeks was a very good friend of David Chandler. So I told John, like, Pablo will come and definitely talk about how he has proven Chandler wrong. And John said, no, he's not going to do that. So I was like, okay, if he does that, you will have to buy me dinner. Of course, he came here and that's what he talked about. So John bought me dinner. That was great. So, equilibration, and you can read about it. It got really ugly. It shows like the petty side of scientists just kept fighting. They could have argued, but it just became hideous. So equilibration matters. And what we need to understand is how did we prepare our system? So and the answer here really lies in having 0 external magnetic field. How did you get to a system where you have 0 external magnetic field, right? Because in reality, something is going on, right? There is always the Earth's magnetic field or something. So in order to prepare this, you have to take it to a lab condition where you turn off the magnetic field, right? So the question is, when you prepared the system and you turned off the external magnetic field, was it slightly positive or was it slightly negative before you turned it off? And that's where the answer lies. And that's where it changes from 1D to 2D to 3D, okay? So what we are going to consider our system is prepared And you also need to prepare it, right? You prepare it in an ordered state. In order to prepare something in an ordered state, you need to apply an external magnetic field to begin with. Otherwise, you will never have it in an ordered state, right? So the question is, as per this argument, if you prepare it in some ordered state, and if you study it long enough, each and every copy with a negative sign should be equally likely, right? And what we are trying to show is that it matters how did you prepare the ordered state system. So consider our system is prepared by application of an external magnetic field H. And let's say H is more than 0 for now. The same argument will work if H was negative. Okay, we assume H is more than 0. And this field is gradually turned down and brought to 0. So mathematically speaking, we are going H goes to 0, but from the plus side, right? If you remember your calculus, this is the notation we use. When you have a function approaching 0, are you approaching 0 from the negative side or are you approaching 0 from the positive side, right? So this is approaching 0 from the positive side. So if I was to do this, let's think about our partition function. Q is going to every microstate e to the power minus beta in u, right? So I can think about something I will call a restricted partition function. So what do I mean by a restricted partition function? So the partition function goes to every microstate and sums up e to the power minus beta in u. But let's say I want to define a partition function which sums up e to the power minus beta in u only for specific values of the magnetization. Okay, so for example, so mathematically speaking, I would write it as q tilde. It's the restricted partition function which depends on m. You go to every microstate, and if you're doing an integral, you would have a Dirac delta function, but now we are doing a summation, so we have a delta function, and you see whether the magnetization in that microstate is the same as m or not. Okay, so you're restricting the sum, and then you multiply it by e to the power minus beta in u. So m could be anything. For example, you could have q tilde equal to 0, that would be going to every microstate and doing delta of m nu e to the power minus beta in u. So you would calculate the partition function only for those microstates where m nu is 0, right? Or you could have q tilde of 84.5, right? Then you go to every microstate, you look at the magnetization in that microstate, which is summing over all the spins, and you see whether that is equal to 84.5 or not. If yes, then you count e to the power minus beta in u. If not, you don't count it, right? So that's the restricted partition function. And here delta of m nu minus m is equal to 1 if m nu is equal to m, 0 otherwise. And if you did it numerically, you will have to have a bin, you will have to be careful in how you actually calculate it, things like that. So now if I ask you, what is the probability of observing the system with some magnetization m? That probability will be nothing but q tilde of m divided by q, right? Q is all microstates, q tilde of m is restricted microstates, right? So that's what you're doing over here. So this ratio now tells me what is the probability of observing this system with a given magnetization, okay? Okay, so we can write it down mathematically. So P of m, the probability of observing the state with a magnetization m is going to every microstate. Effectively, we could have written this down without using the language of restricted partition functions. It would just be going to every microstate, calculating whether m nu is equal to m. If yes, you take that with a weight of e to the power minus beta nu, and in the denominator, you go to every microstate and take the weight of e to the power minus beta nu, right? So those who did Wang Landau, this is like histogramming. That's what you're doing with a weight. So if we have a partition function, we can connect it with thermodynamics, right? We are doing canonical ensemble. So the log of partition function is the Helmholtz free energy. So we can now define the Helmholtz free energy of the system with that magnetization, that A tilde of M is defined as minus KBT ln Q tilde of M, right? What does this free energy mean? Since 60% of you, and through correspondence, all of you are now experts on Jarzynski's paper, Chris's paper, you just studied things like this, right? So A tilde of M1 minus A tilde of M2 gives the reversible work needed to change the system from magnetization M1 to M2, reversible. As you saw in Jarzynski's relation, it's very hard to be reversible. So in general, the work done will be more than this difference, right? So we're just talking about second law of thermodynamics, right? Second law of thermodynamics says work done is always more than equal to free energy difference. If you do it reversibly, those two are the same things, right? So this is the reversible work needed to change the system from M1 to M2. So if you plot this thing, how's that going to look? And this is why I'm talking about this thing in an intuitive manner, just trying to give you a sense for why this puzzle happens. It will make sense. I'm not being super mathematical here, but I think that's okay for this. So I'm going to plot this A tilde of M versus M for different systems. So for a 3D or a 2D system, it's going to look like this. Like this. It will be symmetric, okay? And it has to be symmetric because that was the puzzle. So if you calculated the average magnetization from this A tilde of M value, you would get it 0. It's not going to happen. But this is where the preparing the system business comes into picture. This is true exactly at zero magnetic field. But let's say in order to prepare the system, you applied a magnetic field which is positive. So if you applied a magnetic field which is positive, then A tilde of M is going to look something like this. It's like the red curve, right? If you have H more than 0, that's how it's going to look like. You're preferring the system to be in a certain magnetization, right? The big magnetic field is saying, stay in my direction. Now, if we turn H down, what will mean is this curve will start coming down, right? But it will still, as it comes down, it will still have some value, right? The hero of this problem is this barrier. If you brought it down and you trapped your system, let's say you prepared your system in the positive magnetic field, external magnetic field scenario, then what does that mean? If system prepared with H more than 0, spins lie in this basin, right? Everything is positive, the average magnetization is positive. And there is a barrier, let's call this A star. This barrier is stopping the system from going from the right side to the left side. So as you turn the magnetic field down, you get a symmetric curve. But because the barrier has some value, you cannot just jump from right side to left side, right? Thermal fluctuations will take you, but the barrier is going to have a certain value. And the answer to our conundrum lies in the following observation, that the value of this barrier depends on the dimension. In Pearl's droplet argument, we saw that irrespective of the domain that you create, where does the barrier come from? The barrier comes from the boundary of the interface that you have created. And then Pearl's droplet argument, that barrier was not changing with the size of the domain, right? So you could make a bigger and bigger domain. How would the barrier, so the question I'm trying to motivate here is, how would this barrier depend on the number of particles in the system or the number of spins that you have flipped? In 1D, the Pearl's droplet argument showed us it just does not depend. As n becomes very large, this is just, anyone remembers the number we got in the Pearl's droplet? Max and Rachel had a factor of 2 off. So maybe they remember. 4J, right? 4J does not depend on N. But when we went to 2D and 3D, that number depended on L, the domain length, right? So it turns out in 1D, this A star is 0. In 2D, it depended on the length of the domain, right? Length of the domain means it depends on square root of N. In 2D, length is square root of N. In 3D, again, it is the edge of the domain, and that is, and I'm being a bit hand-wavy here, but if you think about it, it'll make sense. The whole idea being, and if you're worried about 1/2 and 2/3, it's just the surface area argument. The point being that the barrier A star, irrespective of how you prepared the system, once you get trapped somewhere, you have to cross Mount Everest to go to the other side. While in 1D, there is no barrier. You can just flip. So if I am to draw this A star versus M curve for different dimensionalities, it will look as follows. A versus M for 1D will look like this. There's no barrier. It can just go back and forth. In 2D, it will look something like this. In 3D, the barrier becomes even higher. Okay, so this is 1D, 2D, 3D. So, and that's why, and the peak should be right at the origin. I'm sloppy in drawing, you know by now. So effectively, the barrier A star becomes much higher than KT in 2D, 3D, and it traps the system in a broken symmetry configuration. So you expect from the underlying Hamiltonian that the system should be symmetric, but you don't have it. It becomes a broken symmetric phase. And one of the most beautiful essays in science is an essay called More is Different by Phil Anderson. It's available online. You should all read it, where Phil Anderson rants about it. Particle physicists hated Phil Anderson, like from the bottom of their guts, from their hearts, from their kidneys, whatever, because they thought we want to do the standard model, right? We will keep finding the next quark, next lepton, next gluon, and we will understand life. And Phil Anderson said, no, that's not going to do it. Funky things happen as you go to more dimensions, as you study things longer, as you add more particles, more is different. So he said, it's rash of physicists to say that biology is trivial because we know particle physics. Yeah, next time you have an argument with your boyfriend or your girlfriend, just tell them, like, I know you're trivial. It's just made up of atoms. I understand you. That doesn't work that way, right? There are many complicated things. These are emergent behavior that happens when you study things, large number of particles for long enough time, you get the system to be trapped in broken symmetry configurations. And Ising model is the first example that you can see of broken symmetry. In fact, the fact that solids exist, crystalline material exists, is an example of a broken symmetry configuration. That's where it comes from. So this is broken symmetry. In our class today at 5 p.m., I will talk a little bit about order parameters. I will talk about correlation lengths, things like that. Thursday's class, I will do renormalization group theory, which won't be on the final. If you're totally stressed out about the final, feel free to skip it, but just come. It will be something, it might be, you might not study it ever again. So it's a nice opportunity to come and learn something which is also quite beautiful. So see you today at 5 p.m. If the door is locked, just send a message to any of the chemical physics, biophysics students. They will be able to let you in.